So hi, my name is Aakash. I'm here from Etsy, and here's Sheila. We both are here to talk about our unified real-time ML data pipeline and how that helps us in training and serving of machine learning models. So what's on the agenda today? We're gonna start with an introduction to ML at Etsy and what are some of the unique challenges facing us. We're going to talk about our unified feature store and how that's enabling a lot of interesting work. And then we're going to go into the details of how a feature logging pipeline helps with training and serving of models. And finally, some of the real-time ML applications that are enabled because of it. So Etsy's mission is to keep commerce human, and we're a global marketplace for unique and creative goods. We're a home to a universe of special items, from like unique handcrafted items to vintage treasures. So we're essentially a global marketplace, and just to give a sense of scale, we're about 82 million active buyers and 4.5 million active sellers, and about $10 billion of transactions took place on Etsy in 2020. So I hope that gives a sense of what we're dealing with. And our job at Etsy is to connect the sellers and the buyers, so who have different passions and creativity. So buyers are coming to Etsy with a particular vision in mind, and sellers are using their creativity to provide products for that. And the question is, where is machine learning in that? And actually in a lot of places, as we will find out. As an example, if you search for planters on Etsy, you get about 300,000 results. And there's no correct answer, right? So there's a huge diversity in not only the functional aspects, so like the color or like the price or where this listing is from or when is it going to ship, but even in things that are not as discrete and cannot be described in a concrete, discrete label. So these could be aesthetic, style, many latent features, and we'll see how a feature pipeline needs to account for that. The second point I'll make is that when you come to Etsy, I might like the Pokemon planter, Sheila might like the llama one. So our individual preferences are truly what need to be taken into account. So there's a big need for a personalized shopping experience. So overall, what's so unique about the ML challenges here? We have about 85 million items, which are ever changing. We're driven by personalization. As I mentioned earlier, our items are not just different in functional characteristics, but also in the latent and the non-discrete space. And that's where personalization helps us show the users the most relevant items. A key piece on all of this is real-time machine learning, because a user's preferences also change in real time. I might come to Etsy looking for a particular item and then be inspired by what's shown to me and start looking for something else. So overall, we're saying that real-time machine learning and personalization, these two are the keys in surfacing relevant content. And our models have to be personalized, so take into account user preferences that are changing, and real-time adapt to real-time preferences as well as aggregate trends. So we're gonna discuss how we've designed a real-time data pipeline to achieve that, and over to Sheila now.
Hi, thank you, Aakash. So hi everyone, my name is Sheila. I'm the tech lead for ML Pipeline at Etsy, and I'll be going into details about our real-time machine learning pipeline solution. Well, first, I'll be talking about the feature store, which is a central part of our solution. It's implemented with a columnar structure for easy scalability, enforced with a type schema, which we'll talk about in just a bit. The goal of the feature store is to provide us a centralized way of storing and accessing features for training and serving purposes. There are many designs that go into this to make it easy to work with while maximizing the feature freshness and the quality, which is really important for model training. Well, it all starts with storing various types of features. Could you go back to the previous slide? There are two major types that we consider. One is called batch features, which is generated and updated daily. The other one is called real-time features, which gets constantly updated throughout the day with often sub-second latency. Both batch features and real-time features can be aggregated over some time window, like the last 30 days or the last 30 minutes. And they can also be characteristic features, for example, the status of a listing, which can get constantly changing. So for those, we stream update into our feature store once detecting a change on that information. We made our feature store a centralized place for all features so that it can be shared across products, such as recommendations and search, and many duplicated efforts can therefore be avoided. When designing the table, we put different types of entities. For example, we have user entities, we have listing entities, and we put them in separate tables. We chose a NoSQL database for its dynamic schema and horizontal scaling. We apply the database with a logical structure so that each feature source is mapped to exactly one column family, as you can see from the graph. Each column family can house several features coming from that same feature source. This design will benefit us in many ways. The major benefit is the asynchronous feature update. Since each feature source is grouped into a single family, updating a particular feature source is made much easier to our feature store. From the diagram on the upper right, you can see that different feature sources can get ready at various different times. Once a feature source is ready, we immediately start the asynchronous upload to update the associate family in the database. This would optimize for feature freshness and also make the on-call process easier, since each feature source can now have a direct owner for contact. The other benefit from the columnar structure is its ability to follow the typed schema we use for our features. So, well, first of all, why do we need a schema? A schema can help us in many ways, and in particular, help us automate a lot of processes and validate data for quality control. This schema we created was shared across all applications so that we were able to read and send data between different applications smoothly. On the right-hand side, we show a simplified example of our schema for a simple feature family. So the family name would be basic, and there's two features housing under the family, title and price. And from the graph, you can see how that's related with the database structure in our feature store. Adding and testing new features are also easier with the help of the schema. So to do that, we start with updating our schema with a new feature family called new family here. An automated process will then pick up the schema change and register a new family in the database sandbox for testing. Before a new feature source is uploaded, it would also be validated against the schema to avoid sending bad requests to the database. Another important automation triggered by the schema update is the feature metadata template. So this contains important information about what that feature is, what's the source of the features, name, type, the status, etc. And the developer of this feature is responsible for filling them out before officially adding the features to the store. We also expose these metadata files to a web page for increased visibility and readability for customers. As a result, our schema plays an important role to connect multiple applications and processes together. It helps make our life easier in many different ways, from database control, like the one I talk about, registering new columns in the database, to data validation, like how we are validating our data against our schema, and from facilitating feature access, some of the schema generates automatically some functions to fetch the features, and all the way to promoting documentations like the metadata files I mentioned. Now that we've talked about the feature store, let's dive into training and surveying using the feature store. Specifically, we'll be touching on feature logging, which is a solution we implemented to overcome a lot of challenges we faced in the traditional development environment. So first of all, training data is formed with two major parts: attribution labels, which can be like a purchase or a click action at Etsy. And there are also features associated with the attributions. For example, user features and listing features. So user feature in this case can be like a contextual features, and listing will be our candidate. So listing would be the candidate features. Traditionally, there are two ways to generate training data. One way is to do multiple feature source join from different places and join that together with the attribution label so that we can generate the training data. And the other one is to join with a daily snapshot feature store, which already contains those multiple feature sources, and join that with the attribution labels. So both of them are completed offline in a batch job fashion. Although it makes sense flexible for the development, it actually poses some major challenges when it comes to model training. So first of all, it creates a training serving skew due to the often inconsistent feature processing between training and serving. And secondly, it's not possible to access real-time features easily, while being more real-time is our goal. And finally, either method also poses some unique challenges like high cost for multi-joins, adding new features are difficult, like it just makes them not so ideal to solve our ML problems that we are interested in. So we introduced feature logging as a solution to overcome those challenges. The goal of feature logging is to log the exact features that are available at the inference time to train our models. By logging features in real time, we brought this offline process, like this offline batch joining fashion stuff, to online key value fetching. Moving it online makes it possible to access real-time features. This ensures us to record the most accurate real-time information available at the time of inference. Being able to generate this process on real time also enable us to get real-time training data, which Aakash will talk about the applications later. The diagram shows when a request comes in, the reactive system will talk with the feature service and then pass the features to model layer. So that's the inference process. And it will simultaneously trigger a request to the feature logger so that it's able to log features through Kafka and then save it. Here comes the important part of how feature logging helps us solve the problem. So feature logging happens asynchronously right after the inference. So it's able to capture the same feature used for the inference with minimal discrepancies. Therefore, minimizing the training skew that we talk about is one of the major challenges we had. Not only can it record features used in inference, it can log basically any other features available during the time of the request. For example, a user's recent actions for personalization needs. Because feature logger lives inside the reactive system, which talks with all essential services other than the feature store as shown in this graph, like candidate service, model layer, it can also log information from those services. So for example, it can log candidate information such as candidate scores, candidate sources. It can log models information like the model scores and stuff. If you have an ensemble model, it can even log the intermediate model scores and things. Plus, it has access to the request itself, so it can log request metadata for debugging purposes. So all of those informations would help with downstream analysis, and it can power many explainable ML applications. So both feature logger and the inferencer needs to talk to the feature store at request time. So for that purposes, we use a smart feature selector to determine the exact list of features we want from the database. The feature selector is automatically generated based on a model config or a logging allow list. The right-hand side shows an example of our allowed list, where features are represented in a way very similar to our schema and to how our database is constructed. The feature selector then simply extracts this information to build a database filter shown on the right-hand side of the arrow. Schema also plays an important role in the inference and logging process. It guards against bad data when we attempt to log features to Kafka. It also generates deserialization functions and many other functions that get shared between the inference and logging process to ensure consistent data processing to further minimize the skew. Now I'll pass back to Aakash to talk about real-time and personalization applications that can be implemented with our pipeline.
Thank you so much, Sheila, for that great overview. I'm gonna dive into what this enables, particularly in terms of real-time and personalized machine learning applications. So the first one is that in-session personalization with feature chaining. So initially in my talk, I talked about how user preferences are changing in real time, and they're changing very quickly when they're on the site browsing through items, whereas listing content is relatively static. That's not changing as frequently. But there is a need to match these two, right? And we incorporate users' recent interaction and compose or combine them with pre-computed static features. And this helps us better capture what the user's shopping mission is. So we'll dive into an example of that. So an example of this is a feature where, say, we want an average embedding of the last 5 items a user has clicked. So let's first see what all is involved here. So the embeddings could be pre-computed. They could have been generated by any different algorithm and could represent a particular listing, right? So there are 80, like I mentioned, there are 85 million listings. Each has an embedding. We've generated that. We've stored that somewhere. For a user, we need their last 5 clicks. And we can collect that. We're collecting event data, and we need to combine those two now. And the aggregation function is how we help combine that. Now, why are we doing this? Traditionally, the listings, the embeddings only represent the listing, but we would like to incorporate users' recent information to also represent the user in the same embedding space. And this is extremely powerful because then you can better match the users and the listings that best serve their needs. So an example architecture is that users' clicks are coming into the site. We have a streaming service that's ingesting all those events. We're chaining or we're composing those with pre-computed listing features, and then we're getting chained features. So more concretely, we get the last 5 items of a user. We combine those with the embeddings to get the average embedding of the last 5 items. And that becomes an input into our personalized ranking model. And of course, we're using the other features from the user feature store or the query or listing feature store that we've talked about. But by doing this chaining, we're able to incorporate the composed features and combine real time with pre-computed features. Moving on to the second application of real-time feature logging is drift monitoring as well as validation. So because we are logging our features from the reactive system in real time, as Sheila mentioned, we have built a simple Kafka stream application which can ingest these feature logs. And this is extremely powerful for validation purposes. So by logging these features in real time, we can see, is there any error in those feature logs? Are we adding some, are we missing any values? Are the feature values out of range? So we can catch these bugs or errors, any distribution outliers very quickly. Our teams can react, and we can fix the pipelines very quickly. But one of the applications which we're starting out with and which we're very excited about is this feature data monitoring and drift monitoring. So understanding the feature distribution and how they're changing on a day-to-day, and being able to explain our models with it, that's like a key here. And that's where I think a lot of explainable AI systems can also plug in, and they can ingest this real-time data stream. Cool. Okay, and moving on to one of the actually my favorite application of the whole real-time ML pipeline, which we've started on, is a bandit application. So traditionally, multi-arm bandits are used to dynamically allocate site traffic to different variants. So what do I mean by that? I basically mean users are coming into the site, and we can use static A/B tests traditionally to figure out, oh, do we show them bucket A or bucket B features? But in a multi-arm bandit, we can dynamically adjust it. We can say today 40% will see this, tomorrow 50% will see this, and we can adapt to their needs over time. These bandit applications are very useful and powerful for in search and recommendations land, particularly in candidate selection and ranker model selection. We'll talk about candidate selection just now. A key thing here is that contextual bandits are even more powerful because they take into account the real-time context. They're not learning context-free. They're not learning a global setting, but they're able to incorporate what this user wants, what's available in real time. And that really helps us, serve them even better. So we'll see that in an application. Okay, so diving in. So the problem is for candidate selection for recommendations. So on the right side, we have a first pass candidate selection. So we have different candidates. So we have visually similar listings that have been purchased together, or TF-IDF listings. So these could have been generated with different algorithms. So like visually similar listings have been generated with embeddings. Co-purchase listings have been generated through, co-purchase matrix or count. TF-IDF, traditional information retrieval. So these are candidate sets, and concretely, they are a pre-computed list, right? So you're saying for user A, these are the top 100 candidates. For the user B, these are the top 100 candidates. So you have these candidates pre-computed. You have a second pass ranking model, and this ranking model can rank these listings. So it can tell you, hey, if I give you top 100 listings, which ones to show to the user. Now, what we would like to do is figure out what is the combination of this candidate set that we need to surface to our users. And specifically, we don't want to just come up with one global combination. We want to be able to do it at the user level. And that's where contextual information comes in. So this is where a contextual bandit system helps us, where we're going to fetch the user features from the feature store, which becomes a source of contextual information. We're going to fetch real-time streaming features, which also becomes a source of contextual features. So that's similar to the chained features I just talked about. And how are we learning this bandit? So if you look on the left, we're getting the attribution events, which are the clicks, cart ad, or purchases. And then we're getting our users' queries, which are the ranking models. And so based on those, we're able to log our features, we're able to get our attribution events, and we're able to learn this mandate to best learn the, what are the candidate set combinations. So yeah, that's a simplified view or a high level view of how we're, using contextual bandits for candidate selection problems. So to summarize, there are many applications of our pipeline, starting from sharing of features between different teams and models, real-time data validation, which I talked about, especially explainable AI as being one promising one, in-session personalization being personalized features such as chained features, training models across products. So that's something which I didn't dive into, which is that you can share, because we have a standardized schema, we can share our training data between different models. And the two of the future applications, one of which we dived into was contextual bandits. So how we're using contextual features to serve, personalized candidate sets. And one really promising one in the future is online learning. So because we're logging our features and our attribution data in real time, we can now update our models more frequently. So hope this was a great summary and this helps folks, get a sense for how real-time and personalization is key at Etsy, what our feature store structure is like, how we're using feature logging to train and serve models, and some of the applications. So if you're interested to learn more, please check out our blog at etsy.com and code as craft.
Excellent. Thank you, Aakash and Sheila. You all got time for a few questions? I think we still got a few minutes on the clock.
Sure.
Sure.
Yeah. All right, let's do it. There's some good ones coming through. And I must say, you took some seriously complex subjects and you were able to distill them down into very understandable bite-sized ways. So props to whoever was doing the design on this. That was very well done. First question coming through is for Sheila. How do you store on disk the flat view of all features coming from the same family? Or sorry, do you store on disk the flat view?
Cool. I'm happy it's a yes or no question. So when we have like single feature family, that basically means the single feature source. So that means like all the features from that source is generated under one job. So yeah, short answer, yes. After one feature source is generated, those are saved on disk in some format before we can upload that to our feature store. And afterwards, we can delete it once we get a snapshot of the whole feature store. Well, we still keep a snapshot of the feature store just for some of the offline analysis purposes and stuff. But yeah, they did get stored on disk in some format and then get deleted once the TTL is passed.
Excellent. So another one for you, Sheila. So the stream and batch jobs load the data into a single database that users read from to retrieve their features for both online and offline workloads. What database are you using?
Okay, interesting question. So the database definitely gets both real-time features and batch job uploads. But the way to access those features currently are only online, like through online inference or online feature logging. In terms of the database that we're using, I don't know if I can say it, but currently we use Google Cloud Bigtable. Yeah.
All right. And if you can't say it, we can edit that out later. Don't worry. Just tell us. No problem. So there's one more. Maybe Aakash, you want to give it a go. Have you observed any correlation between model performance and the freshness of features derived from real-time data?
Yes, we definitely have. I don't know how much I can explain without revealing actual results. But we've definitely seen. Okay, let me just leave it at that. That there are definitely some aspects of the site where this matters more. So there are some models. So if you've like added an item to your cart and then you're doing it, then it's like, hey, we really know what you're looking for. So then it matters more. So there are definitely some models where it matters more, some portions of the site where it matters more. And yes, we've seen the real-time features as well as fresher features matter more. Yes.
All right, last one, and then we'll go to the break. Is there any limitations you have experienced due to computational complexity of contextual bandits in real time?
I mean, definitely, it's a very big task to monitor them, and that's what we're like excited about. Like, it's just the replayability of this is actually a really big challenge. That how will you? It's an online system which is going to learn in real time, but you also, how are you going to learn the policy per se offline? That's where a lot of the challenge is. So it's not just as much about like enabling it in production, but also like being able to learn that and observe that. That's where a lot of the investment goes in.
Excellent. Okay, I lied. There's one more, and we still got a minute, so I'm going to ask it because people have been loving this talk, as of course they would. This has been super informational. Mike's asking, how do you manage cost attribution, and or do you do you do that at all?
We definitely are managing. So one of the things about having a centralized feature store is that we have individual feature owners. So that's on the feature generation side, where we can see like which team is generating the features. But I think the question, if I'm understanding the question, the real point of the question is that, you're building a lot of these things once, and then you're trying to add, you utilize them in different models. So the cost is then shared across those applications. We've made some efforts on attributing and understanding it fine-grained. I would say that we're not as fine-grained as we would like to be, but we're definitely on that path. Yeah.
Yeah. Asking about the dollar cost.
Yes, exactly.
So excellent. This has been amazing. And Aakash and Sheila are both in Slack. So if you have more questions for them and this incredible talk, go ahead, get over there, get into Slack and ask them. Thank you both for this. This was awesome.